and share my screen. Awesome. Welcome everyone to another fun and engaging session with Deep Learning Adventures. You can find us on Meetup as well as on YouTube. We record all our sessions where we talk about data science, machine learning, and deep learning in general. We've been fortunate enough to go through different challenges, or what are called micro challenges through Kaggle. And we have a few more left. And today we're going to talk a little bit about a specific one that's more related to optimization than model building or data prep as we've seen in the past. I'm lucky enough to be joined by many friends around the world, so we went through a short introduction session. Thank you everyone for sharing a little bit about your background. And looking forward to getting to know each other better, forging a stronger community, and working together on interesting problems. As I mentioned, all our sessions are recorded. I'll be posting a link pretty soon on our chat, so you can join both the Slack channel that we have as well as our previously recorded session, where you can see we've been pretty busy with this Kaggle Mini Courses on Python, machine learning, an introduction to deep learning, feature engineering, SQL, some geospatial analysis. Robert did a great job with us covering the first micro challenge, Blackjack Microchallenge, and then Dimitri is going to cover for us the second micro challenge, which is on airline price optimization. We have a couple of more sessions before we finish this Kaggle challenge. Let me go to our calendar. So we have a get-together next time. Next week, it's not recorded. It's just a get-together. I highly encourage you to check it out. And then in January, we have the last two sessions related to Kaggle, which is computer vision one, as well as an introduction to game AI and reinforcement learning. I have a surprise for us on the 27th. I invited a few guest speakers for us to talk about some of the interesting projects we've been working on. And we have an open session on the 20th that we're looking to fill up. Cool, with that said, I'll be posting some links. This is the micro challenge site on Kaggle under kaggle.com/learn microchallenges. And I'll be handing it over to Dimitri, our great friend, who will be talking about the airline price optimization.
Yeah, thanks, George.
And thank you, Dimitri, for putting together this great notebook. Looking forward to hearing more about it.
Absolutely, yeah. So, okay, can you share? Can you see my screen?
Yes.
Yeah. So, as you said, George, this is the second micro challenge from the Kaggle Mini Courses. This is about airline price optimization, and this is not actually a data science per se topic. It's more about algorithm theory, optimization, but still, I think it's interesting. It was an interesting topic for me personally. So the Kaggle page itself doesn't have any data. It just has a short explanation of the problem, and then they have some, framework. They basically provide some helper functions for us to evaluate what we create. So I decided, instead of working here, I decided to create my own notebook in Google Colab, which is, slightly more convenient than Kaggle shell itself. So the challenge is asking you to imagine that we started a new startup that helps airlines set ticket prices. The objective of the startup is to maximize the total revenue that an airline can get from a given flight. And all we have as an input when we start the challenge is basically two numbers, right? The days until the flight and the number of seats available. That's all we have. So as I said, the objective is, of course, to make as much revenue as possible from the flight. And the instrument with which we optimize is this thing called a pricing function. So each day we decide, for how much are we going to sell the tickets. And so depending on that, we get some daily revenue. And so that continues for as long as the flight is basically available. And so that builds, your total cumulative revenue. Now, there are a couple of rules that, govern this whole thing. First of all, the relationship between the quantity and the price is given by this, rather textbook-looking relationship, which many of us may remember from the economics classes. So the relationship between the price and the quantity is given by this this formula. So there is some demand level, and the price and quantity basically add up to the demand level. This has nothing to do with real units or how the thing works in practice. So this is basically a useful or a handy arithmetic to for us to imagine different situations. So the Kagglers chose this specific formula for us to basically balance and then find the right the right point on the curve. We don't know, importantly, we don't know the demand level, and so demands each day has a different demand, and the demands are drawn from a uniform distribution, between 100 and 200. And each day before we set the price, we learn the demand. So, it's one date maybe 150, another date maybe 170, etc. And so each day, given that demand that we learn, we need to decide on the right price to set. And a couple more points. So the seats, of course, are available to sell until the flight leaves. Basically, whatever we don't sell yesterday, we can still sell today, but we can't sell more than the flight capacity. So those are basically the entire rules of the game. And so if we look at this price quantity relationship, we can see that for a given demand level, basically, let me try to annotate here. Yep. So for a given demand level, so the demand levels are these red lines. If we set the price here, we can sell Q2. If we set the price, for example, slightly lower, like here, right, we can sell slightly more Q, etc. But if the demand is higher, we can sell the same quantity for a much higher price. Basically, we can sell the same quantity Q, the same quantity this one for a larger price. And so basically, if the demand would not be random, if it was, say, 150 constant, then the optimization, there still will be place for optimization, but it will not be a difficult problem, and it would probably be able to solve it analytically. So there will exist a closed form solution. But because the demand is random, we need to balance. Like, if the demand is high, we should probably try to sell more tickets on that day when the demand is high. When the demand drops, we sell slightly less. So the whole exercise is about how we find this right point to maximize our revenue. So let me erase that. Okay. So we start with global variables. The challenge itself on Kaggle has 100 days as the maximum length. So there are flights that leave sooner, but the longest is 100 days, and the most capacity is 100 seats, so 100 tickets. And as I said, the demand level is drawn from a uniform distribution with minimum 100 and maximum 200. Now, I just recreated a brief cumulative revenue helper function that basically, given the pricing function, which we come up with, any pricing function, it recursively, iteratively applies that pricing function, finds the quantity that we can sell, builds the revenue, and then applies the same pricing function for tomorrow. So this is there is nothing particularly interesting here. It's just iteratively applying the same pricing function to get the cumulative revenue. So there are a few ways to approach this problem, right? So when I looked at this before even thinking about dynamic programming or anything about like that, I thought, what if we just took a very simple approach, like if we sell equal amount of seats every day, basically spread the existing seats evenly and see what happens. And so this is the first function I wrote. This basically pricing function linear, which says whatever the whenever you are, basically you have the days left and seats left, and so divide the seats by the days, and imagine the demand level will be even, basically. And so I simulate the pricing function for 10,000 days, 10,000 runs, I'm sorry. And this is what we get. This is basically a Monte Carlo simulation for this pricing function, right? And this is the result. And if you look at the cumulative revenue, 14,900, what it says basically, if you have 100 seats, on average, you sell for $149 per seat. So that's the average revenue per seat you get, which is logical given that the mean or median demand is 150. So basically, the demand is 150. In order to sell at least one seat, you have to set the price at 149. And so that's basically, it tells us that our intuition is correct. Basically, we sell on average each seat for $149. So that's the basic benchmark. Now then I thought, can we do something better? Like if we learn that day the demand is high, can we sell slightly higher, slightly more than the linear model? And if the demand happens to be low, let's sell slightly less. So try to maximize our revenue that way. And this pricing function adaptive, this is exactly what it does. Basically, I introduced an ad hoc coefficient called adapt, which is, if the adapt is 0, it's basically the same linear, but the higher the adapt, the more you try to sell on the high demand day, and the lower you try to sell on low demand day. So basically trying to adjust to this random demand. And I just took adapt level 2, and again ran a 10,000 simulations, and this is what we get, like $156 per seat for this particular adapt level 2, which is slightly better than the linear. And then I tried the same thing for different adapt levels. So basically, this is 156 is basically as good as it gets. It starts declining. So apparently, if you get too greedy and try to sell too much, you forego the opportunity to sell at good prices later on in the process. So trying to capitalize on the first good day may not be as good an idea. But these are heuristics, and on the Kaggle page, people have used a lot more different heuristic rules, like if the price is in this range, try to sell this much, and different these types of piecewise solutions, basically trying to be as adaptive as possible and try to take advantage of the high demand days. But yep,
Clarification question, Dimitri. So you mentioned
sure.
that on the days where the demand is more than 150, you lower the price a little bit. Is that the goal, so that you can have more seats sold?
When the demand is higher, and suppose you have like 20 days left and 100 tickets left, right? And so on average, the linear function would give you 5 tickets per day. So if you sell 5 tickets per day, that's your linear. If you see that demand is high that day, you don't sell 5, you sell, say, 6, okay? And if the demand is low, 120, 100, you don't sell 5, you sell 3 or 4. So that's the whole logic of this one. And so, but so these heuristic solutions and piecewise solutions, they are of course suboptimal because they they don't try to find the global optimum for this problem, which actually exists. And because the search space is not enormous, it's only 100 days and 100 seats and 100 demand levels. We can actually afford doing something called dynamic programming, which I'm going to talk about next. So before just applying the dynamic programming to this particular challenge, I thought it might be worthwhile spending a few minutes just discussing what it is in general. So basically, it doesn't have anything to do with the programming itself. It's just an algorithm. It's a term that describes a class of algorithms. And the approach is basically when you have something sequential and complex, try to break it down into stages or into components, and then find the optimal solution for the subproblem for a component, and then store it instead of every time recalculating it again. Just build this massive or maybe not so massive table of pre-calculated, pre-indexed optimal solutions, and then access those solutions as you need it. So that's basically the whole idea of dynamic programming, and it's used, as I learned, quite extensively in different, parts of computer science. Like, for example, in Levenshtein distance, the deciding, the shortest distance between two words. How do you convert one word into the other in with the shortest amount of additions, right? The insert character, delete character, etc. So this is called Levenshtein distance. And you apply dynamic programming for that. The shortest paths problem, knapsack problem. So basically, many types of problems that have the beginning state and the end state, and a multitude of trajectories or paths between the 2 points. And the objective is to select the best one. That's your very traditional problem for dynamic programming. So why is dynamic programming actually effective for these types of problems? Because it converts the exponential time of the original formulation of the problem into a linear time. And so, for example, even our very basic Fibonacci, if we think about it, if we don't think about storing the previous results, if we just try to solve the problem recursively, so Fibonacci 6 is 5 plus 4, and 4 is 3 plus 2, etc., etc. If we just approach it from top to bottom, then the tree grows exponentially, right? And so the recursive formula would consume, basically exponential time and maybe exponential space. But the dynamic programming formulation only consumes linear time, because actually we don't need this whole tree. We only need each element once. And so if we move bottom up, and then we calculate Fibonacci 2, and then Fibonacci 3 and 4 and 5 and 6. We don't need to keep all these, all these parts of the trees in the algorithm. We just keep, one linear array basically. And I have, I just tried here. Building first the recursive solution, which is, the wrong way to go here. It takes Fibonacci 20 takes 1.64 milliseconds per loop. And Fibonacci 20, so basically, because this is, this is a binary tree, right? So it's to the 20th, like around a million calculations, around a million steps here, right? In Fibonacci 20. And if we want to calculate Fibonacci, 40, this is already, forget about this. It will not be able to calculate. Now, in contrast to that, we can do dynamic programming thing, right? We can first create, some the array, this memoization, basically the starting array, and then each time we access the array, if we already calculated that, just return that. If not, calculate from the existing and store. And so, basically, this is the whole dynamic programming idea. This line. And if we time it, it works 158 nanoseconds per loop, which is like already like 10,000 times faster than the recursive, just because, this is a linear thing that only has like order of 20 calculations. So in this pretty simple idea, we can apply to, as I said, many types of problems, and this airline price optimization is one of them. So before going into the algorithm itself, I thought, maybe we formulate it in a bit more sort of strict way. So what we want to do is find the optimal price in this range, right? So the range is pretty sort of self-explanatory from the economic perspective. We don't set the price lower than demand minus seats, because at this level we just sell all seats at one day. Like, for example, if there is only one day left and we have to sell off all seats, basically that's the minimum price we can imagine. And the highest price is the demand level itself. And if we set the price at the demand level, we don't sell any seats, right? Because the quantity is demand minus price. And so if these two guys are equal, the quantity is 0. And for example, we might want to actually do that. If the demand is too low, we might set the price at the demand level so that we don't, sell any seats at the low price. And then this is the math explanation of the dynamic programming idea, right? So for each day, what we want to maximize, what we want to optimize is the cumulative revenue, this thing here, which is a function of the days remaining and the seats remaining, which in turn is the sum of today's revenue. This is the Q times P, plus some expectation of what is the next day optimal revenue. And the next day optimal revenue, we of course don't know that because it's a random variable, but we can calculate the expectation of that random variable. And so that's basically all we have to do. Basically working backwards, say for the first day or for the last day before the flight, we calculate this expected maximum revenue, and then for the second to the next, we add today's revenue to arrive at at the bigger cumulative revenue. And let me pause like that right there, and please let me know if there are any questions, because this formula is key to understand the algorithm going forward. Do you have any comments on that, George? Because I think you also tried this problem, right?
Yeah. So just to clarify, the price could be any real number, right? It doesn't have to be integer. So in your quantity, which is demand minus price, you basically want to come really close to the demand level, but not at the demand level itself. Otherwise, your quantity would be 0. So maybe you want like a small deviation from the demand, like P minus some small epsilon or something, or demand minus small epsilon.
Yeah, because the seats that the quantity is integer, and the demand level is integer too. Just they made it integer for some reason. Then the price is also integer. So if the demand level is 150, and you have to sell 2 seats, you just set your price at 148, and you set you sell your 2 seats. So in this particular case, the price is also integer. Everything is integer here, by design. Not that it's it's not our choice. But the raw price is integer, but the expected cumulative revenue is not integer. It can be a real number.
Question.
Sure.
Yeah, Dimitri. So, by the way, what's the objective of this optimization? Just to, is the cumulative revenue static?
Yeah, to maximize the cumulative revenue over the entire period. So through all the days you have.
Yeah. So what do we expect from the expected demand cumulative revenue function? Does it gives now, for assume this is operational. So what's helping the sales agent? Is it just giving a plan, like quantity plan? Functionally, what the agent is expecting from the optimized level. So is that setting the number of quantity or?
Right. So what you actually have control over is the price, right? So this thing is the only thing you control. So the price determines your quantity. So the quantity and the price determine today's revenue, right? This Q times P.
Right.
But then today's Q determines how many seats you have left for tomorrow. And so you can go greedy and sell many seats, and you have little seats left for tomorrow. But the problem is whatever Q you decide today, you will have a certain Q for tomorrow. But the problem is you don't know the D for tomorrow, right? And so the second term takes the average expectation of your optimal revenue that you left for tomorrow over all possible levels of D, which is unknown. And so that's where the expectation comes from. Is that your question, or?
Yeah, it might be early, but yeah, it's fine.
So I think SFA was asking from an operational side, like how do you use this? Do you give this pricing function to the sales agent, and then the sales agent basically sets the price? If you want to operationalize this, I know this is a theoretical project, but.
Well, I think, in this particular exercise, what we actually produce in the end is a full pre-computed matrix of all the optimal prices. So for whatever seat and day combination you might ask, you have the optimal price to choose. And that's the theoretically, the best optimal price, basically.
I think it's really interesting how with these 2 micro challenges, this one is so similar to the Blackjack Microchallenge in this regard. When I presented that, presented it as a system of linear equations that you could solve without using matrix methods by just solving one at a time because they were arranged in a certain form. But that is basically equivalent to just dynamic programming in disguise. So that blackjack problem was essentially like formulating a matrix of the scores of the player on one hand, the dealer value on another hand, or no, the player score on one hand and the number of aces, I think. But it was just the exact same concept where you could optimize simply by solving a series of equations. This one's a little bit more complicated, and I think you've laid out the dynamic programming portion of the problem really well. But I thought it was just interesting to point out the parallels there.
Yeah, cool. So let's see how we actually do this. Let's look at the last day, because last day is easy, right? So whatever we basically have at the last day, we have to sell. Basically, you know, the day the flight leaves, we can't sell any more seats. So so that's those are the ranges. The the days range, seats range, and demand range, which we'll be using down in the algorithm. So basically, what I did here is creating this maximum revenue array, which this is only for the last day, right? So which goes through the entire seats and demand combination, and just selects, you know, the best revenue. So basically, the question is, you know, what price in this range, which range again is demand minus seats and demand, right? So which price gives us the best maximum revenue? And so, you know, what we do is, you know, for each combination of the seats and demand, we find the best revenue. That's all it does, this whole thing, because it doesn't have this expectation of the future part. All we have to maximize is this Q times P. So that's what we're doing. And this Q times P on the last day gives us this, you know, this manifold. So this is the demand level. This is the seats left. Like for example, if there are no seats left, whatever the demand level is, you know, you don't get in the revenue. If you have all the seats still on the first day, that's, you know, depending on the demand, you get a different level of the different revenues, right? And if you notice, you know, this manifold is flat over here. That's because, you know, if you have the lowest demand, and then you know, starting from certain amount of seats left, it doesn't make, you better not sell them. Basically, it comes from the fact that, you know, on this, I'm sorry, on this diagram, if it so happens that you have a lot of quantity, actually the optimal point for the maximization of P times Q is right in the middle of this curve. It doesn't make much sense to go lower, because, you know, your P times Q gets smaller. So that's the as low, the price can only be as low as demand times 0.5. Yeah, so that's why it's flat. But basically, you know, this is on the last day, you know, we learn the demand, we know the amount of seats, and we choose the optimal price to get, you know, this much revenue. That's pretty simple. Now the question is, you know, before we learn the demand for that day, so talking about the expectation, looking from the 2 days before, right? We don't know the demand, so on the last day. So, what should we do? How should we approach? Now, 2 days before, we only know, how many seats we have left for the last day. But, how should we go about the maximization of the total objective, right? And so that's where the expectation comes in play, right? So basically, we take the expected revenue for each seat level taken over all possible demands. So basically, if we average this manifold in this direction, over all possible levels of demand, so that's what we get. Basically, this is the expected maximum revenue in the last day as a function of only seats, because we don't know the demand level yet. So this curve is what we have 2 days before looking at this equation. So 2 days before, we will be optimizing, the 2 days before current revenue plus the expectation from whatever seats we will have left for the last day. So I hope this is clear.
There's some questions on the chat. Christine, Alexander, if you have any feedback or comments, feel free to unmute yourself. Otherwise, we can follow on chat if you want.
I think my core problems with the problem is all the simplifying assumptions that I made to frame it in this way. But I think that's helpful to make the problem a little more abstract. Sometimes you want to focus on one part of the problem, and solve that, and then break down the problem. So it seems like they've broken down the pricing problem and focus on this one particular piece. Mm-hmm. I guess I'm curious to see when you start to bring in more real variables. So your demand each day, you can probably forecast that. So then you have a forecasting component in this problem. But of course, that makes it more complex, and you can't really focus on the optimization challenge.
Right. I would assume. I've come across problems of, I would say, probably same nature in warehousing logistics many years ago, and many random variables, and still you have to optimize your stock and revenue, and they ended up not the company, but the consultants ended up doing something like Markov chain Monte Carlo simulations, etc., because you can't calculate the entire space, right? Mm-hmm. This is, as there is no sense to no point in doing something like MCMC here, because basically you can calculate with brute force the entire search space, right? And yeah, I agree. This is a oversimplification.
Mm-hmm. You could also, you can also frame this as a Markov decision process, which basically says you have a sequence of states, and each state depends on the previous state.
Yeah.
So I'm sure there's people who've taken a reinforcement learning approach to this problem.
Right. Yeah. And if you make it maybe a couple hundred flights and many more seats, etc., so it can very easy get out of control, and you can't count on actually calculating everything, right? So yeah. So once we have built this foundation, basically, all we do is replicate this process, going backwards from the last day of the flight to the day zero, when we make the first decision. Basically, we optimize the today's revenue plus our expectation of the next day's best revenue, given the amount of seats that we decide to leave for that later stage. And so for all the previous days, including the last day, I built this this cycle, which is some adapted or optimized from a nice Kaggle notebook that was already there. And basically what it does is, it's the brute force calculation for the entire grid of days left, seats left. For each of those possible combinations, we actually imagine, all possible demand levels, and then, for all demand levels, we calculate the best price and the best revenue. And this part is exactly like algorithmically this formulation. So we take, all the prices in this range, we calculate the quantity, and then we calculate today's revenue, and we add today's add the optimal revenue to get today's optimal revenue. And so this is basically exactly that. So for this price, we calculate this, and then if the revenue we calculate is actually better, then we replace the revenues with this better found numbers. So that's basically it. And so it runs for whatever, about a minute.
Question.
Yep.
That line 25, Dimitri, is that
Yep.
the average price using a uniform distribution? Is that how you get the expected max revenue?
Yeah. So the basically, for each demand level, we get the maximum revenue for that demand level, and then when we calculate the analog of this thing, we basically, the expected revenue the day before is, we add we basically build this expected revenue the day before from these chunks of maximum revenue for this given demand level, divided by the length of demand level is basically this is the expectation part, right? So because it's uniform, I should have written 1 by the the 1 divided by the length of the demand range times max revenue. So it's probability times the value, but so this was just this was shorter.
Awesome.
So this is the probability. This is the if it's from another distribution, you just replace this with the probability.
Awesome, thank you.
So the total number of computations in this loop is what, about 100
million?
Looks like there's 4 nested loops, right? And each
4 nested loops, right? Yeah.
Each one of them goes about 100 values.
No, this goes the days, seats, and demand is 1 million, and this is smaller, right? Because this is not 1 million. This is not 100. This is a smaller range. Maybe on average, like I would say 10, 15. We can actually, let me.
Well, it looks like it's just based on what seats is, right?
Just hold on a second.
The range is going to be basically equal to seats, or the number of terms is going to. So it looks like it's about 100 to the 4th over 2, or 100 to the, or 10 to the 8th over 2. Number of times it will loop.
Let's try.
I guess we have to wait 50 seconds for it, though.
That's okay. Yeah, you know what? Let me run this, and then we'll.
I'm trying to decide if there's a way to optimize that quadruple for loop. It's a little harder because different pieces are dependent on each other,
Yeah.
but I'm sure there's a clever way to optimize it because for loops, that's pretty bad.
I think we, days and seats probably no.
Yeah.
Demand.
Demand range, you probably could, because it's for the same number of days and seats, right? I admit I don't know the notation well enough to really think
I think,
about it.
for each demand and seat combination, demand is drawn, independently from a uniform distribution. So you may not explore the entire search space, but I think you can do something with the combination of demand and price, not to go through all of the values.
I suspect that for every combination of days, seats, and demands, that price is a function that is what do you call it, concave, right? So it increases on one side, decreases on the other. So you could probably just try a few values and quickly get to the max, like a gradient ascent sort of thing.
I maybe I'm just the price, the maximum revenue for the day is definitely concave or convex. It's definitely simple, but
so you might be able to get away with a log of
but the other component, so the best revenue for the day, yes, but the combination of the best revenue of today and the expected maximum revenue from tomorrow, that's I'm not sure is it behaves nicely.
Right.
So yeah.
Then I think in practice,
Here it is. Yeah. So wow, 52 million calculations. Yeah.
This is for a small problem. In practice, you'd probably be, I don't know, I imagine with a real problem, you might need some sort of network or some other learned function to try and approximate this. So I imagine in practice, maybe, so if we can frame this as a Markov decision process, right?
Yeah.
We could, and so anything that's a Markov decision process, each day you make a decision. That's very similar to the idea of like reinforcement learning. And so maybe that's how you might solve this in practice. And I know we haven't done the Kaggle challenge on that, but that would be my guess as to how it's solved.
Is there a Kaggle problem?
Yeah. There was a Kaggle mini course on reinforcement learning that we're doing.
Our last one.
Yeah.
In January, yeah. So maybe we can revisit it after that.
Yeah, I volunteered to do the section on deep reinforcement learning, which I haven't done before, so I'm excited to do.
Awesome. Thank you, Alexander.
Great. Yeah. 52 million calculations. Yeah. I mean, brute force is only, applicable in the small problems. So one thing I also decided to add is this, when we have, basically, when we calculated this entire cube, how does the days left, seats left combination work out actually in terms of the expected revenue? And so, for example, if we have 100 days left and 100 seats left, there is this upper right corner of about $185,000. So, no, I'm sorry, $18,500. And so, this is the maximum revenue that we can get. And then, of course, it decreases with the number of seats left. It decreases with the number of days left. But interestingly, the days are not as important as the seats, right? Like, for example, in this region here, basically, it doesn't matter, if you have 100 seats left or if you have 100 days left or 80 days left, if you only have a few seats, like, for example, 10 or 20, basically you have plenty of days to sell those seats at good prices. And so that's why your optimal revenue does not change much. You can only, sell for that much, right? But the smaller the amount the days, basically the sooner the flight leaves, then it becomes it becomes more critical, right? And so that's why we see this interesting shape. And finally, what I decided to do is to take this the maximum, the point of the days and seats, basically 100 days, 100 seats, the longest flight, and calculate and see what we have calculated by brute force. So this is the 18,574. And then I thought, what would be the equivalent of that if we just, if we haven't calculated it, if we take just the optimal prices and run them through simulation and see, how the shape looks like. And this is basically the Monte Carlo for that same process. And what I have is basically the same number, which is basically, this theoretical maximum expectation is, you could say it's an unbiased estimator of this process, of this underlying process. But I thought also, the standard deviation is pretty large, right? And so that might explain, George, why we get different results on Kaggle.
Yeah.
This is the best as you can do. Apparently you can't do any better in expectation, but $2, $3, $5 here and there, it always has this range. So, but I thought this is interesting that despite that the average demand is 150, and as we saw, with the linear demand, with the linear pricing function, you only sell for whatever 150, 149. Actually, if you do clever and you adapt, you can sell at 185. Close to maximum. Basically, your price is in the range of 100 to 200, but you sell at 185. And finally, I compare this to the Kaggle pricing. So coming back to my Kaggle notebook, so they have this handy function called where was that? Yeah, score me. So basically, yeah, you use score me, and it gives you a few expected revenues for 200 flights from a few configurations, and then they take the average of those revenues, and that determines your optimal score, basically. So that's what they do, and I try to replicate that basically here. But there is no point in replicating. You just, because we have pre-calculated everything, we just take the values from those points in our cube, and we get just the revenues, and that's what we have. And the numbers are not exactly the same. Like for example, the average of those four, I have 7603, and they have 7574. I don't know where the difference comes from. I tried to look around, but didn't get the answer. So Kaggle, it might be this 200 thing. It might be something else. They have in the score me algorithm, but I'm pretty sure it's basically essentially the same. So basically, what we have here is the algorithmically the optimal solution. So I think that's it for the challenge. And for me, I mean, this is a pretty artificial and small problem. Alexandra, I totally agree with you. Just for me, it was interesting because let me explore a little bit how the dynamic programming works, and to learn about this few other problems. Not exactly a data science exercise, as I said, but still was an interesting piece. So please let me know if there are any questions. Yep.
I would counter argue that dynamic programming is data science. but it's like a building block. So if you read a textbook on reinforcement learning, you'll probably see one of the first few chapters on dynamic programming as one way of solving many of these types of problems. But of course, as we just saw, there are severe limitations to it.
One thing that distinguishes this problem from much data science is the fact that it's everything is known, right? There's no uncertainty about the probability distribution. They told you exactly what the distribution is. In data science, typically we're guessing the distribution based on what we can observe, which is just a sampling in the real world of that distribution.
Are there any questions in chat, George?
Yeah, let me. I don't see any. I had a question for you, Dimitri. I noticed you used a new module that I haven't used in Python yet. If you go all the way to the beginning, I think it was called partial function or partial fun.
Yeah. One.
Yeah, partial, that one.
Yeah, this is a cool thing actually. So it lets you actually, you know that functions are like first-class citizens, right? You can pass them as arguments. You can do whatever with functions as objects in Python, and so this thing allows you to actually pass a function as an argument with some parameters, and so I'm not sure. I don't remember where exactly I used it. Oh, yeah, I think, okay, here. So remember this adaptive function had this arbitrary parameter that, I just came up with. And then if I want to pass that adaptive function as a parameter to my, cumulative revenue simulator, I want to add, I want to add the parameter value. And so I can't do that if I, unless I use the partial. So that's the only way I can pass the function with the parameter.
Mm-hmm.
That's handy. I have definitely passed dictionaries of parameters plus functions around. So this is a neater way of doing it. So you can just pass it into the function itself rather than like handling all these extra things.
Right.
Nice.
Yeah, that was a newer thing I learned, today. So cool. Thank you, Dimitri. Any other modules I used? I saw you use some really cool visualization modules and libraries, but other than that.
It's the standard 3D thing, this guy. But Matplotlib is for 3D things. I heard, it's not the best thing. I just, needed to do something quick. So that's
Mm-hmm.
Okay.
Cool.
Then. So I'll stop sharing then.
Awesome. Thank you, Dimitri. That was very, very
Thank
useful. Just remember the number you got, right? 7603. That was your highest average revenue, right?
Yeah.
Cool. I think it's the highest I've seen so far. That's why. I can share some.
But the Kaggle is 7574, so it's the same. So it, you can get that's the maximum, and people just use the same dynamic programming, got the same number. So it's.
So is that like a theoretical maximum, or is that like an expected maximum?
Yeah. Because it breaks down into, because the expectations are independent from each other, and breaks down into additive steps. Mm-hmm. So you maximize expectation over the entire path, breaks down into additive steps. So, but if the problem had interdependencies, and if it was not, this Markov property, then it would not be the case. So then, it would be more complex.
Cool. I'll share quickly some other approaches that I came across. Robert and David, feel free to share your approach as well. So first of all, in the exercise, there's a typo in terms of the quantity demanded, the way that it's defined. It should be demand minus price instead of price minus demand. And then based on the different approaches, yeah, I tried different ones. The easiest one is just to sell 10 tickets a day. Another one is sell a percentage of tickets left. Another one is uniformly spread them out based on the days. That was your heuristic approach, Dimitri. That was the third approach. And then what I noticed on the Kaggle forums is that somehow people figure out these different heuristics or different levels, that if my demand is less than 50, then I only sell, portion. I spread out a quarter of this uniform spread out. If my demand is a little bit higher, less than 100, maybe half of that. If my demand is less than 150, I'm 75% there. And if my demand is more than 150, I uniformly spread it out. There was some other one based on completely heuristic, or I don't know the numbers. If days left more than 14, just return 180 for like how, when, how, or more than 2, or if it's 2 or if it's 1. That one got an interesting one. And then actually one of the Kaggle instructors, he has another solution on dynamic programming, and he breaks it down. And I think that's the function that you mentioned, Robert, right? That for a combination of seats and I think a given demand, then there's a maximum amount of revenue you can achieve.
Right. So for a given curve, it should be possible to find the maximum only selecting a few points. But I think, as Dimitri said, for calculating expectations, you probably need the entire curve.
Got it.
Okay. No, this one is this parabola is the simple one-day optimization. Just if you have P times D minus P, that's the parabola you get. And so,
Yep. Yeah, P times demand minus P. That's exactly the quantity. Yeah. Then, then use this Q and V function. I'm not going to go over the code, but I just wanted to show you the final results here. So if you sell just 10 a day on average, I was able to get a revenue of 6,000 total revenue. If I sell only a percentage of tickets left, it didn't achieve that much, about 5,000 revenue on average. And then the heuristic ones in the end, which is a little bit higher, the dynamic program one, the 10 particular is 75.58. And you mentioned the maximum is 75.74, right? So I guess it's close to that. And I'm curious how your approach was 6.7603. So that's interesting to me. That would be even higher.
That's what I said. Was the difference between Kaggle and the two price. Their scoring function is not transparent. They probably have some random seed, and so yeah.
Yeah, it's probably not deterministic.
Yeah, not.
Score me, got it. Okay, cool.
It is interesting though how the very simple heuristic from Juntao Deng really only misses it by $100 there.
Yeah, and his approach. Let me go back to it. There's a lot of heuristics like that on Kaggle forums, like a combination of days left, or it was mainly on days left. And what is this formula? Where did that come from? Yeah, that was interesting. Robert or David, did you have anything to share with us, or?
Nothing. No, sorry.
Okay. What about you, Robert? Sorry, you're muted.
Oh no. No, this covers it very well. I didn't do anything beyond any of that.
Awesome. Okay. Yeah. Some more discussion on the forums. Cool. Thank you, Dimitri. That was very, very useful. I encourage you to also check out the notebook and maybe share it on the forums. I'm pretty sure people will find it interesting as well. Awesome, friends. There's no comments, feedback, questions. I just want to do a quick plug-in for the next session and a few upcoming sessions before we wrap up. I don't see anything in the chat. Cool. So for next week, we're just going to do a get together. There's a picture I took today of my guinea pigs. I was trying to decorate their surrounding a little bit. No recording, no slides. Just get to know each other better and have a good time before the holidays. We'll take a break for, let me go back to our calendar, for the last week of December. And then we'll resume on January 6th. We'll do a computer vision Kaggle Mini course. And the last one is the reinforcement learning one that we're going to explore. Awesome. I'll post the recording tomorrow. I'll stop the recording here and I'll just leave the floor open for discussion if anybody wants to hang up. But other than that, thank you, Dimitri. This was super useful. Thank you for the detailed explanation. And thanks for the good questions, everyone. And hope to see you next time. I may stop the recording here.